This is my physics capstone interview for James Frank. My name is James Frank, and along with my colleague Gustav Hertz, we are responsible for a series of experiments that established the existence of discrete energy levels in the mercury atoms. Originally, the goal of our experiment was to relate the quantum theory to the selective photoelectric effect that was discovered by a colleague of ours named Robert Pohl. Later on, we were able to prove the excitation energy of the mercury atoms. Our results would help lay the groundwork for the validation of Niels Bohr's atomic model. My joint papers with Hertz inscribed our names onto the rolls of history for physics. Our discoveries in quantum physics, as well as my moral integrity on scientific and political matters of the day, are what makes me one of the few recognized physicists in our field today. To this day, I find this fact very peculiar, since as a boy, one of my teachers regarded me to be one of very little promise. Before Hertz and I began our research, in the year 1900, John Townsend, a physicist who worked under the great J.J. Thomson at Cambridge, began publishing a series of papers where he was investigating the collisions of low-energy electrons of gaseous molecules. Later on, Hertz and I found several flaws in Townsend's original theories on the ionization potentials that Townsend found. Townsend assumed that electrons would lose all of its kinetic energy in a collision. This is not at all what we found in our experiment. Now, our collaboration was brought about by a qualitative study of the elastic collisions between electrons and random atoms to see if we could determine their exact behaviors. After careful considerations, we concluded that if we substituted the mercury atom, we could produce more precise results for proving the excitation potentials of electrons. And after we considered this change, first, we had multiple conclusions. First, the collisions of the electrons with the mercury atoms are perfectly elastic for the energy up to 4.9 eV shown in this graph. Second, above 4.9 eV, energy electron is transferred to the atom, but always in quantums of 4.9 eV. And the excess is retained as kinetic energy. Third, the inelastic collisions led to the emission of light at only the resonance line of 2,500 or so angstrom in the mercury atom, and the energy loss of the electron was equal to the quantum energy of that line. These combined results demonstrated the way quantized energy transferred from kinetic energy to light energy. It was at this time that we used our findings to reform the underlying theories that Townsend proposed. With further investigation, we found that in noble and in non-atomic gases such as helium, electrons below a critical velocity lost little, if any, energy in collisions and diatomic gases. Collisions resulted in large amounts of energy loss with higher electron affinity. That is, the higher they went with the shell, in the higher they climbed in the atomic shells. Excuse me. This, in combination with the connections between the ionization energies, which is what allowed the link between the electron collisions and the quantum mechanics to be found. One thing that we also found was the connection to Planck's constant was the resonance line for the quantum frequency, when it equaled 4.9 eV, we were able to find that it equaled Planck's constant. And this could not be ignored because it now validated Planck's original findings in his original theories. We were able to prove this through all of our graphs and our measurements that we published. Since Bohr's atomic model had not been published, but only a year before ours, we were not able to adequately account for it in our papers, our original papers, our first published papers, I mean. So we accounted for it in later papers, but instead chose to use J.J. Thomson's papers and atomic model to validate our original our original measurements. We chose to use that as our original atomic model, our original basis. In years to come, when other physicists were building on our work to further quantum mechanics, Walter Gerlach of the Stern and Gerlach experiment would remark that without these fundamental discoveries found in the Frank Hertz experiment, we would not be able to make our quantum connections to the excitation of the spectral series that we found. We were able to show that the possibilities of such experiments had to offer the experimental conditions needed for the successful releases of future physicists' work. And it gave them a place to build, and it also opened doors for the future of physics in the whole of quantum theory, quantum dynamics, all of that. Our experiments occurred at the Physical Institute of the Friedrich Wilhelm University in Berlin. And in 1911, Hertz had just moved to Berlin to complete his PhD under the director of the institute, Heinrich Rubens, who at the time was researching the infrared absorption in carbon dioxide. After I finished my PhD at the time, I too was working under Rubens in the same laboratory, aiding him with the exploration of the electronic structure of atoms, which we had used to facilitate the findings. We had partially used to facilitate the findings of our research that was foundationally critical to a lot of our finding, to a lot of our discoveries. We needed a lot of both mine and Hertz's research at that time. We required that. And soon after that, Hertz and I began our research together. The laboratory we used was the same laboratory that all of the university assistants used to instruct the laboratory experiments for the undergraduate studies. And we were all such a tight group of enthusiastic enthusiastic PhD students that we had passionate discussions about our observations. We shared all types of ideas, our apparatus contraptions, and how everything was built and made, and how we had it all calculated out, and what resources we were using, and why we used them, and where we were using them. and why we chose to use them that way, what theories we were choosing to use. As a scientist, I am fascinated with the breakthroughs of other visionary uh, scientists and all of their efforts. Shortly before Hertz and I began our work in 1911, I was fascinated with the work of Marie Curie when she was nominated and awarded for the Nobel Prize in Chemistry for her discovery of the radium and polonium elements. One thing that amazed us the most was that this was her second Nobel Prize. She had previously won it in physics just a few years prior. Wow. The Nobel Prize in Physics that same year also went to a colleague of ours, William Wynne, for his contributions amending Max Planck's original study in black body radiation, which several of us had also used previously in several of our works at the time. Black body radiation, as well as the quantum energy equation that we had used in our studies before. It was fascinating. In 1913, around the time, we were also publishing some of our defining work. Heike Ohms achieved the Nobel Prize in Physics for his developments in the properties of materials, which led to the creation of liquid helium. And later on in 1914, when we were revising our work for the Bohr atomic model, Theodore Richards of America won the Nobel Prize in Chemistry because he was able to devise a methodology to properly determine the weights and the atomic masses for the chemical elements of certain up to a certain point for the periodic table up to what had been discovered up to that point. In the same year, Max von Laue, a fellow physicist of mine, was presented with the Nobel Prize for his discovery for the diffraction of the X-rays by crystals. I found that discovery very fascinating for its time. In the same time frame, towards the very end of July in 1914, tragically, I happened to read in one of the newspapers at the time, I read of the assassination of Archduke Ferdinand by a Serbian, and this caused worldwide tensions to greatly exacerbate overnight, nearly, and it was really sad. Um, uh, and when Austria later on declared war on Serbia as a means of retaliation, my home country at the time, later on I did immigrate as a means to escape all of the tensions later on. But at the time, I was still living in Germany. My home country was still Germany. Uh, Germany allied itself with Austria and entered the war. And so I volunteered as a private in the German army, and I was able to eventually work my way up to lieutenant. But I'll speak more on that in a minute. Um, we unfortunately had to stop at this time. Me and Hertz had to stop our work uh, up to this point and just publish what we had. Um, and there were a lot of scientists at this time that had to, throughout the international scientific community worldwide, France, Britain, Dutch, the Netherlands, um, very many Nordic countries, Austria, Italy, they all had to stop their scientific research, and it was very catastrophic for the international scientific community. And one thing that was also very catastrophic to the scientific community was when very many prominent German scientists um, in Germany decided to sign the Manifesto of the 93 that basically denied Germany's accountability for any effects um, or any accountability that Germany could have taken to mitigate um, the war. And it hurt the international scientific community. And it was something that those wounds would not heal for a long, long time, and they would not heal until the very end of the Cold War, and that is what is absolutely sad. Is it took us a long time as a area as that part of the world to heal. Um, you know, what started in the teens ish of the 1900s and still didn't heal until years later. In the war, I was seriously injured in battle while trying to lead my men, and was bestowed with the Iron Cross, and was promoted to the rank of lieutenant. And I was still accomplished in the army, despite there being many anti-Semitic tropes in the German army. As I was a Jew, I was a practicing Jew, and I was Jewish by heritage. Even despite this, I was still able to gain the respect of my men that was in my command. And I did enjoy this still, to the point that it left a vivid story in the mind of Max Born, one of my long-term friends that I grew up with and that I served with, who was also a physicist as well. He recalls how I had the great respect of my friends that I served in the war with, and that how I protected my men and how they also respected me. After the end of the Great War, numerous scientists, when the war was over, after the Great War, when the war was over, numerous scientists applauded us for the successful discoveries that we had made for our contributions when studies for the developments of quantum physics continued, especially after such a long, drawn-out interruption in scientific progress had ceased. And now, in 1919, since there had been such a cease for now 5 years or so, which, given the fact that there was, publications every few months, and we go from every few months to there being zero for 5 years, that's a big drag. That's a big drag. When that was picked back up, we were the recognized group of people. We were amongst the recognized group of people. Excuse me. As physicists, we're influenced by the likes of many, countless and brilliant thinkers, visionaries, all different types of philosophers, physicists, numerous types of scientists. And in our present day, when we were developing our work, you had the likes of many brilliant mathematicians, Albert Einstein and Hilbert, and numerous different ones publishing constantly brilliant papers and loads of stuff. The Stern-Gerlach experiment came afterwards, after ours, but then before us, you had the Einstein experiment, and then about the Einstein's photoelectric experiment. Before that, you had, Bohr, and then, later on in the 20s, you had the Solovey Conference. So we were well influenced by many brilliant minds that had many lasting impacts on all of us, all throughout the German science community, the German intellectual community, as well as numerous international studies. But me and Gustav Hertz, Hertz and I, were the only ones involved with our projects. We were the only authors of our papers. And Hertz was the one that possessed the fine-tuning skills for operating the apparatus, developing the apparatus, and he commanded a greater understanding of how to compute the, mathematics. I was more of the intuitive nature physicist. He was more of the computational physicist. In 1914, when we were publishing our findings up until that time, the Great War had already started. We were able to, just in time, be able to prove our final theory on the ionization by collisions solely by Hertz's mathematical skills. He was able to deduce it just in time, and we were able to prove our calculations in that paper by Hertz's abilities. We were later recognized when we were later recognized in several papers, interviews, intellectual discussions that we had over the years for our accomplishments. We both admitted that neither one of us could precisely recall who had contributed what and who calculated, what specifically, and who was responsible for any specific parts of the research, besides Hertz being responsible for the mathematical calculations. Outside of that, and him designing the apparatus, we equally contributed both parts, and that is well documented. We both worked together very well, and very fluidly, and we did that to be able to prove, both of us, that there were no assumptions in our. We did all of that in order to prove that there were no assumptions made in our research. There were no gaps. There was no miscalculations. We both checked over one another's works. We made sure everything was fit together and fit together properly. Before we, before we started our investigations, I was analyzing the electronic structure of atoms and molecules in 1910, as well as the elementary processes associated with the collisions of random atoms. This is something that I was studying with Professor Rubens at the time, and before I had started my research with Hertz. Later on, when Hertz and I had started our research, Hertz stated that had it not been for my prior knowledge, that we would not have been able to complete our calculations without me being able to go back to my previous research and be able to prove we did this under Director Rubens. We did this in the laboratory. Here's exactly where we did it. Here's how we did it. Here's where we calculated it. Here's how we tabulated it. Here's the formulation. Here's our chart. Here's everything. Here's exactly how we laid it out. Additionally, Hertz was able to state that I was responsible for documenting the fact that the collisions could excite the molecular vibrations and the quantum rotations. I was able to supply a thorough analysis of the energy distribution graphs to make it explicitly understood that the electrons lost little energy in the collisions. This conclusion was in stark contrast to Townsend's theories. During our laboratory experiments, I possessed an instinctive response to realizing the relationship between the energy levels, quantum theory, the Thomson model, and the Bohr atomic model to prove that they were all directly related and being able to make all the precise connections to them to make our research one cohesive piece laid together. When calculating the ionization potentials, originally we used the apparatus that was devised by Philip Leonard, but the glass bulb had to be modified. Hertz did not know how to do that, and so he left that to me. And so I was responsible for going to the glass blowing station in the laboratory and modifying with a glass blowing pipe in the furnace, in the glass furnace, excuse me, and blowing the glass pipe and stretching it out and molding it and reformulating our tube. And so that we were able to then heat it and cool it and process it and then put all of the proper materials in it. And then when we put it back on the apparatus, we were able to fit all of the proper pieces down into it and fit that precisely down in there. Our investigations worked marvelous, not only by validating and supporting the work that had come before us, but also by unlocking pathways for further innovations to come afterwards. In our first set of papers, we demonstrated the flaws in Townsend's theories and the assumptions that he made in the critical velocities of electrons, the ionization potentials of electrons, as well as the electron affinity for noble gases. What is so peculiar to Hertz and I is even despite extensive experimentation and documentation that we were able to produce, Townsend refused to accept the fact that we were able to prove the results of his experiments had many flaws in them. And as a result, his reputation as a physicist in the scientific community suffered dramatically, because from here on out, shortly thereafter, we got our Nobel Prize in physics. Me and Hertz got our Nobel Prize in physics, and Townsend's work was very discredited from then on out, and which is so sad, because before Hertz and I published our work, Townsend was doing groundbreaking work. He was facilitating tons and tons of advanced physics and chemistry with Thomson and the laboratory at Cambridge. And after our research, his reputation greatly diminished in the scientific community. In our second set of papers, we were able to provide ample evidence that even for the older atomic models, such as Thomson's, the atoms were able to be quantized, and that their critical electron energies were resemblant to the results found in our original experiment. And thus, even before we had even modified our calculations to accommodate before the Bohr model, we had validated everything that had come before. That is the Thomson model, Planck's um, Planck's calculations, Planck's original theories, as well as the foundations of quantum theory itself. We had validated everything that had come before and built upon it and developed, and not only gone back over it and smoothed it all out, but built on top of it as well and built a clear stairway for the rest of quantum physics to be founded upon, and how that did lay the foundations for the quantum physics community to come. Because the next year, Frederick Linderman was able to take Planck's previous calculations and take our calculations and reevaluate them and come up with a photoelectric formula for calculating the frequency, and just using Planck's original works. And so even then, there were people coming after us doing exactly just what we had done, validating, moving forward in time and opening new doors, and yet validating what had come before. And there were multiple scientists that kept doing that very same thing thereafter, moving forward in scientific achievements and validating things that came forward. Moving forward as in opening new doors, and yet validating everything that had still come before. That's brilliant. Later on, another fruitful, massive achievement that came afterwards in the 1920s was the Stern-Gerlach experiment, when they were performing their study of the quantization of the electron spin. They were able to use our work as well as the work that had come shortly thereafter of ours to develop the quantum magnetization of the atomic model. And so they would not have been able to conclude their work without the research that we had built. These same reevaluations confirmed the accuracy of the Bohr model, as well as everything that had done before. And so, in 1922, with such compelling evidence for the Bohr model, not only our research, not only Albert Einstein's research, not only those that had come before, not only Stern and Gerlach's and Linderman's and Planck's, as well as numerous other countless compelling evidence for Bohr's model, as well as Bohr reevaluating Thomson's model, as well as some of Thomson's understudies evaluating Bohr's model and finding it to be accurate. Bohr was able to be bestowed with the Nobel Prize in Physics in 1922 for his documentation for the structure of atoms, and for the Bohr model that we still use. For the most part, it's been remodified over time, but for the most part, we still use it today. In the late 1920s and 1930s, other scientists and physicists employed our findings when demonstrating the absorption spectrums of the alkali halides in aqueous solutions, which later became known as the electron affinity spectrum of the halide ions. Of course, I could never truly document the full measure of what truly came out of our work, the true validation. I mean, we would sit here for a while truly discussing the 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 accomplishments, the consequences, the logical fallouts, the accomplishments throughout the physics community, all the brilliant projects, the brilliant debates, quantum mechanics, quantum physics, um, relativity, all this stuff that fell out afterwards. That I mean, we would be here all day long, and I mean, that'd be a hard undertaking to see just how far the magnitude of our work actually extended into the scientific community. In the 1930s, when Hitler and the Nazis rose to power and began enacting their anti Semitic agenda, I resigned from the University of Göttingen as a sign of personal protest since I was a proud Jew of my faith and heritage. This was the instant when I transformed from a scientist to a moral leader, one who is motivated to stand up for my people. I could not just stand out. I could not just sit there and not stand up for my moral ethos. I had to do something. And from here on out, from the 1930s all the way through to the end of the war, I assisted many of my fellow Jewish colleagues as much as I possibly could, escaping the regime's cruel orders, as well as finding employment in America, Britain, Canada, and escaping the Nazi regime as quickly as possible. For example, before the war broke out, we sent, Max von Lowe, a fellow physicist of ours, and who had also won a Nobel Prize back in 1914. We sent our Nobel Prizes to Niels Bohr and George de Hevesy in Denmark so that they could hide them from the Nazis, because the Nazis did not like, people that they did not like having gold. They did not like that. So we sent ours, as well as several others, to them to hide. And they dissolved them in a bottle of aqua regia. And what was so interesting was Bohr told me that later on the solution was going on. They were putting the Nobel Prizes in the vials of aqua regia as the soldiers were walking through the streets, so that when the soldiers came into the laboratory, there was nothing but a clear solution sitting on Bohr's desk. That's pretty interesting. And so it sat there for 8 years or so. And so later on, after the war, de Hevesy came back and was able to find the solution. It was in the same spot because no one moved it. It's a chemical laboratory. And he took it to the Nobel Prize Foundation, and they were able to reverse the chemical processes and remake our Nobel Prizes. And so we got our golden Nobel Prizes back. That is an interesting way to escape the Nazis and still keep your moral integrity. In other cases, I sent food to students who were of Jewish heritage and were suffering because they were away from their families, separated from their families. Me and my wife sent clothing to them. We sent money, because I mean we're well off, we're well established, well established scientists, physicists. We're very wealthy. We sent money to them, we sent clothing, and we helped them to get out, and to get back to their families, and to get their families out, because things were starting to seriously get bad as time went on. And with time, uh, I was able to migrate to America and find employment at Johns Hopkins University first, as just a temporary professor, just as a temporary job, just temporary there. And then eventually, I managed to find a permanent position at the University of Chicago. And when I landed there, the American government was running a top secret project called the Manhattan Project. And upon learning of all of my successes as a physicist and a scientist, they instantly gave me clearance, they instantly made me a citizen, and instantly put me in charge of several things within the project, one of which was the chemical division of the University of Chicago's metallurgical research. A short while later, they then appointed me over. They appointed me the chairman uh, of a committee of physicists, biologists, and chemists to decide upon the social and political, uh, moral implications of developing, using, and implementing, uh, and the fallout of using the nuclear bomb. When we finished our report, we submitted it to the Secretary of War, and we urged the American government to consider the use of the bomb as a fatal political decision and not to be as a mere matter of military tactics. We also described the imminent threat of a nuclear arms race, as well as urged for accommodating conditions to be sought within the confines of an international agreement. Due to our report's prominence, it has become known as the Frank Report. I do believe, given the tragic fallout of the latter part of the 20th century, the Truman administration should have taken a different course of action given the conditions that history has played out in such eerily similar fashion that we predicted it to be. And that is a sad tragedy, because we did warn them that this would happen, and they did not listen to us. We did not let that stop us. After the war, unlike multiple of our colleagues, uh, we did not receive appointments to special boards within the administration, within the War Department, the President's Cabinet, um, within the administration as a whole. We did not let that stop us. We constantly advocated for the peaceful change, peaceful international change, and the civilian development of nuclear energy. Uh, and we constantly advocated for the change in the marketplace. We did not let that drag on.